Dear students, today we will study about the electrical energy and power. We know that the charges cannot be passed through a conductor at their own. For moving the charge through a conductor, we require some potential difference or the electric field across the ends of the conductor. Now consider a conductor of resistance R through which a charge flows. If we apply a potential difference, say V, across its ends, the current, let I, flows through it. To understand the potential energy and the kinetic energy of the charges while flowing, consider two points of the conductor, say A and B. Let the electric potential at point A be VA and the electric potential at point B be VV. The electric potential at point A is VA and the electric potential at point B is VB. And as the current is flowing from point A to B, clearly VA is greater than VB and VA minus VV is equal to the voltage applied across the ends of the conductor. Now consider charges Q moves from point A to point B in time interval delta t when current I is flowing through the conductor. Let potential energy of charges Q at point A be UA, and this will be equal to Q into VA, and as current I is flowing, we can write Q is equal to I delta T into VA. And potential energy of charges Q at point B be UB, and this will be equal to Q VB, and again we can write similarly I delta T into VB. So when charge Q is flowing from point A to B, there is a change in the potential energy. The change in potential energy of charges Q while moving from point A to point B will be equal to final potential energy minus initial potential energy. So we can write UV minus UA and this is equal to I delta T VB minus I delta T VA, or this is equal to I delta T VB minus VA, and this is equal to minus I delta T V. Why I put negative sign here? So we can see that VA is greater than VB. The potential at point A is greater than potential at point V. So this is V, and we can say that this is greater than 0, and this means this is less than 0. This is change in the potential energy. And this change in the potential energy is equal to the change in the kinetic energy. This change in potential energy brings change in kinetic energy of charges Q. So if there is a decrease in the potential energy of the charges, there will be an increase in the kinetic energy. So the change in the kinetic energy is equal to I delta T V. Now, change in the kinetic energy means the increase in the velocity and the charges are accelerating. But we know that charges drift with an average drift velocity. Now the question arises then, where this kinetic energy goes? While moving through the conductor, when current is flowing in a conductor, the charges, they accelerate and move, collide with the atoms. And during collision, they transfer this kinetic energy to the atoms. And the atoms, they start vibrating vigorously. That means we can write kinetic energy is transferred to atoms, and atoms vibrate vigorously, and thus the conductor heats up. That is the energy dissipated in the form of heat of the conductor. So we can write Right. Energy dissipated, delta W equal to I delta T into V. And the rate of energy dissipated per unit time is called the power dissipated. Therefore, power is equal to delta W by delta T, and which is equal to I delta T into V by delta T, or P is equal to IV. So this is the expression for the power dissipated or the power loss. Now, as by Ohm's law, V is equal to IR. That's why P is equal to I square R, or P is equal to V square by R. And this is called the power loss or ohmic loss. Clearly, power depends on I and V. Now, how transmission of electric power or the electric energy for long distance is made? Because if we consider the equation P is equal to I square R, or P is equal to V square by R, the power loss or the ohmic loss depends on R. So we study this long distance transmission of electric power. How can we minimize the power loss or the electric energy loss or the energy dissipation or the power dissipation in the transmission cables or the connecting wires? So when electric power is transmitted through the power station, it is very far away. So the resistance of the transmission cables is considerable. So power loss will also be considerable. How to minimize for this? Consider a device R to which power P is to be delivered through transmission cables. Let power P is delivered to device R at voltage V and current I. So P is equal to VI. Now let RC be the resistance of transmission cables from the generating stations or the power stations to the device. The RC is very considerable, it's not very small. So the power dissipated in the transmission cables is equal to I square RC. This is the power dissipation in transmission cables. As I is equal to P by V from above equation. So PC, that means the power loss of the transmission cables, can be written as P square RC by V square. This is the voltage which is applied across the device. So to reduce power loss in the transmission cables, V is taken high. As PC is inversely proportional to V square. That's why long distance transmission of electric power is done at a very high voltage. This high voltage is reduced by transformers. At other end,